Hello children, welcome back to the channel. Today we will be continuing our discussion on center of mass and system of particles, and we have come to an important topic of conservation of linear momentum in a system of particles. So we know that linear momentum will be conserved if the net external force acting on the body, or in this case on a system of particle, is equal to 0, which means, let's say, if F is the total external force, this must be equal to 0. But we have seen that F total or F external is actually sum of F1 plus F2 plus so on till Fn for n particle system, force acting on each of the individual masses of the system of particles, or each of the particles of the system of particles. These forces should sum up to 0, which means that m1 into a1 plus m2 into a2 till mn into an equals to 0. Please remember, this is continuation from our previous chapter or previous video. If you haven't seen the previous video, I would suggest that you first see that video, and then these things will be clear to you. The link to the video will be given in the description below. Okay, so first particle, Newton's first law, second law of motion. F1 is, if F1 is the force on it, m1 a1 will be its acceleration, say, and so on and so forth till the nth particle. Or we can rewrite this as m1 dv1 by dt plus m2 dv2 by dt, and so on till mn dvn by dt equal to 0, because a equals to dv by dt. Since m is a constant and doesn't change with time, we can take it inside, and also we can take d dt outside and take it as a common. So it will be m1 v1 m2 v2 till mn vn. This must be equal to 0. But m1 v1 will be the momentum of the first particle. By definition, momentum is mass into velocity, so d dt of p1 plus p2 till pn will be 0. Since individual momenta are not 0, their derivative will be 0 only if and only if p, which is equal to, say, p1 plus p2, that is, the p is the net momentum, plus pn, sum of all the momenta of all the particles. This must be equal to constant. Which means, if no net external force acts on it, or the net external force acting on a system of particles is 0, then the net linear momentum, that is sum of the linear momenta of all the particles of the system, will remain constant or will remain conserved. This is nothing but stating conservation of linear momentum for system of particles. Alright, so we have seen that net momentum remains conserved, right? It remains constant if there is no external force acting on it. Now, if we go back to the expression for center of mass for n particle system, this is the expression. So, if we differentiate both sides with respect to time, that is drCm by dt must be equal to 1 by m into m1 dr1 by dt. Why I have taken the differentiation sign inside? Because we know that m1 is a constant, masses are constants with respect to time. So this is equal to m2 dr2 by dt plus finally mn drn by dt, which is equal to 1 by m1 v1 plus m2 v2 till m n v n. So we get dRCM by dt will be velocity of the center of mass. So if we cross multiply, m into VCM must be equal to P1 plus P2 plus Pn. That is to say, linear momentum of the center of mass must be equal to the net linear momentum of the system of particles. This is one important result we get. So we have said that the center of mass should behave like the entire body would move if center of mass is that point where, or that position in space where, if the entire mass is concentrated, the point or the particle or the point mass at that particular position will move the same way as the entire system of particles would move under the influence of the same external force. So it is quite expected that if there is no external force, the net momentum of the system of particles must be the same as the net momentum of the center of mass of the system of particles. Let's move on and try to find the center of masses of certain systems. First one is a very simple example. You have been given two masses, 1000 gram and 3000 gram, and their positions, position vectors have been given, and also their velocity vectors have been given, and you are supposed to find the RCM and VCM, that is position or the location of the center of mass and the velocity of the center of mass. To do that, first what we will do is that let's see RCM, position vector of the center of mass. By definition, what it is, we know that it is m1 r1 plus m2 r2 divided by m1 plus m2, right? This has been discussed in details in my previous video. If you haven't seen that video, the link of that is given in the description below. You may please refer to that. Okay, so if it is so, and if you substitute the values and use the proper units, because these position vectors and the velocity vectors are given in meters and meter per second respectively. So the masses have to be converted into the SI, so that will be 1 kg and this will be 3 kg. So now we are in a position to solve this. So what we will have, RCM will be m1, that is 1 into r1. So this is 2 I cap plus 5 j cap plus 13 k cap. This plus m2 r2. m2 is 3, r2 is this. So this will be 3 into 6, 6 3s are 18 plus 18 I cap plus 3 4s are 12, 12 j cap minus 6 k cap. This whole thing will be divided by 1 plus 3, 1 kg m1 plus m2. So if we simplify this, what do we get? 2 minus 18, that is minus 16 I cap plus this is 12 plus 5, 17 j cap plus 13 minus 6, that is 7 k cap, whole thing divided by 4. Okay, or we can rewrite this as 1/4 minus 16 I cap plus 17 j cap plus 7 k cap meter. That will be the position vector for the center of mass. Now what will be the position vector for the, what will be the velocity vector? That is what will be VCM. velocity of center of mass. See, if we differentiate this equation with respect to time, then we get d RCM by dt, which will be VCM. So this will be M1 V1 plus M2 V2 divided by M1 plus M2. Substitute the values and you will get the result. That is, M1 plus M2 is 1 by 4, M1 is 1, V1 is this, so we have 10 I cap minus 7 J cap minus 3 K cap for the first term, plus for the second term we have to multiply this by 3, right? So 7 is a 21 I cap minus 27 J cap plus 6 is 18 K cap. And so if you simplify, we get 1/4 of 10 plus 21, that is 31 I cap, minus and minus, so it's minus 34 J cap, and this is plus 15 K cap. Fine. And this will be given in meter per second. Okay. So we have seen that we can simply or directly apply this particular formula of RCM for simple cases. However, more often than not, the bodies that we come across, the system of particles that we come across, are not such discrete systems. More often than not, what we get is that we get continuous distribution of masses. So, how to use our equation that we have found in the previous video, that RCM is equal to 1 by m integration r dm. How to use this equation to find the center of mass for continuous distribution of masses. That is the type of problem that we will encounter more often. So what we will do, we will see a couple of examples of that now. Now let us say we have been given a uniform rod of length L. What we mean by uniform is that the mass distribution is uniform over the entire length of the rod. So what we want to find is that what is the position of the center of mass of this uniform rod. Now the equation that we have is this: RCM equal to 1 by m r dm. Now, since it's a rod, we can consider it as a one-dimensional object, and so we will be considering only the x direction. We will place the rod such that it coincides with the x direction, or in other words, we will choose the x-axis along the length of the rod. So, if we say this is the origin line, that is O is here at this particular point. The one end of the rod lies at the origin. So the other length will lie at the position where length is L, right? At the distance of L, or its x coordinate will be L. Now let's say we take a small element somewhere in the rod. That element is at a distance of x from the left hand end. And let's say the width of the element is dx, very small length. If it is so, then what will be the mass of this element? How to find this? We have done a similar problem earlier also in my previous videos. So what we have found there is that if we have something like that, say the rod's length is L, and let us say it has a mass of m, then this fraction m by L will give us the mass per unit length of the rod. a unit length of the rod will have a mass of m by L. If L length has the total mass of m, unit length will have this much. We know that, right? Unitary method. If it is so, unit length of the mass has this, of the rod has this mass, then the dx length will have mass equal to this. Mass per unit length multiplied by the length of the element. Here the length of the element is dx. So let's call this dm, the small elemental mass that we needed to use this equation, right? So since we are considering only the x direction, so instead of r we will just write x, that is position along the x-axis of the center of mass, and this will be 1 by m, of course, integration, instead of r it will be x dm. Now we know the value of dm from here, so we can substitute this value. So what we have, 1 by m integration over the length of the rod, right? So it will be 0 to L. Instead of x will be x, and instead of dm we will be writing m by L dx. So m by L being a constant can be taken out of the sign of integration, and we will get this as m and m will cancel. So we have 1 by L integration 0 to L x dx. We know how to solve this. This is a very simple integration. So this will be equal to 1 by L. Then we have x squared by 2 with the limit 0 to L. Substituting the values, we get 1 by L squared by 2 minus 0. Or finally we have x cm, center of mass, position of the center of mass as L by 2, which means the center of mass of the rod will be at a distance equal to half the length of the rod. In other words, for a uniform rod, the center of mass will lie at the center of the rod. Okay, the next problem is to find the center of mass of a hemisphere, that is half of a sphere. Now we have chosen the coordinate axis such that the base of the hemisphere coincides with the y-axis, right, or yz plane, and the dome is towards the x-axis. So it will be something like this, right? This object, it will be standing like this. So what we are having is that in the xy plane, that will be vertical to the board and coming out, the hemisphere is standing. Okay, so if you look at this that way, then this is the yz plane and the hemisphere is like this. If you rotate this, what you will see is that about the y-axis and the z-axis, the hemisphere is symmetric. However, about the x-axis it is not. Okay, due to the symmetry, half of the hemisphere for y-axis, half of the hemisphere is in the positive y direction and half of the hemisphere is in the negative y direction. So the y coordinate of the center of mass, due to the symmetry of the system, will lie at the center. We have chosen origin as the center of the hemisphere, so the y coordinate of the center of mass will also be coinciding with the origin, which means y coordinate of the center of mass will be 0. We can also find it by integrating it from minus r, where r is the radius, to plus r with respect to y-axis. Also, in case of z-axis also, the vertical the axis coming out, again because of the symmetry of the hemisphere, the center of mass with respect to y or y coordinate will also be 0, which means we can write this as y cm equal to 0 equal to z cm. So y and z coordinates are 0. Only thing we need to find is the x coordinate. To do that, what we will do first is that, like the previous case, what we did, we chose a arbitrary x coordinate, x position, we chose a small element. Same thing we will do, we will take a distance of say x from the origin, which will choose a small element. Now here, since a hemisphere is itself a solid object, so at the distance of x, if we draw a line, it will cut the hemisphere, right? So it will be like this. Okay, and if we want to take an element of thickness dx like this, this element will be in the form of a disk. Can you visualize this? If we take this surface and then cut a slice out of it, we'll get a shape of a disk, right? So this will form a disk, and the thickness of this disk is dx. Okay. Now let's say m is the mass of the hemisphere. Mass of the hemisphere is m, and let's say density of the material of the hemisphere is rho. So to find the mass of the element, this element dx, the dm, what we need to find, notice is that this element is itself actually a disk, right? Having a radius equal to this much. Let's call this y. Okay, so y is the radius of it, and it has a thickness of dx. So dm will be pi y square, area of the disk, multiplied by dx, the thickness of the disk. Whole thing multiplied by the density. Volume into density will give you the mass. Now, if you look at the geometry, if I connect these 2 points, origin to the disk, this will be the radius of the hemisphere. Okay, so this is a right angle triangle. So r square must be equal to x square plus y square, or we can say y square equals to, what will be y square? R square minus x square dx, and then rho will be here. So we are now able to find the expression for dm in terms of x only. Now if we have to find the center of mass or x coordinate of the center of mass, what we'll have to do, we'll have to take 1 by m and then integrate it over the entire x variation, that is from 0 to this end. This end will be at a distance of equal to the radius of the hemisphere. So we'll have to integrate it from 0 to r. What do we have to integrate? X into dm. If we substitute the value of dm here in this equation, we will have 1 by m integration 0 to r. Instead of x will remain x, and then we have pi rho r square minus x square dx, or we can rewrite this as pi into rho by m for the time being. Okay, then what we have, integration 0 to r, multiply x and r square x minus x cube dx. Now we have found this equation in an integrable form, which will be very easy for us to integrate. That will be equal to pi rho by m integration. So we have r square into x square by 2 minus x to the power 4 by 4. Whole thing from 0 to r. That is to say, from this what we get, xcm will be, these terms will be there, pi into rho divided by m will be there. If I substitute r here, r square into r square, right? So r to the power 4 by 2 minus, again r to the power 4 by 4. This is the first term, substituting r. This minus, if you substitute 0, of course it will be 0, and then minus 0. So the second term of integration will be 0. So we are left with this term only, which will be pi rho by m, r to the power 4 by 2 by r to the power 4 minus, so this will be r to the power 4 by 4. Fine. Which will be equal to pi rho. Now what is m? M is the mass of the hemisphere. In terms of density, how do we express mass of the hemisphere? M, hemisphere is half of a sphere, so for the volume of the hemisphere will be half of the volume of a sphere. What is the volume of a sphere? 4 by 3 pi r cube. So it will be 4 by 3 divided by 2, that is 2 by 3 pi r cube, and then rho multiplied by the density. So we write 2 by 3 pi r cube rho into r to the power 4 by 4. So this will cancel, pi's will cancel. So we are left with 3 will go into the numerator, 4 to the 8, and then r cube to the power 4 by r, that will be r. So x cm will be this 3 r by 8. So the RCM or the coordinates of center of mass will be 3 by 8 r 0 0, because y and z coordinates are 0. So that will be the position of the center of mass of the hemisphere. Let's now take up the case of a right circular solid cone. What we mean by that is that the cone is solid. The cone shown here, let's call this, or say A, let's call this D. This cone that has been shown is a solid cone. So, and let's say its base radius of the base, this radius is r, and it has a height equal to, say, h. We have to find the center of mass of this. Again, it's a symmetric object, please remember. So what we are going to do here is that we place it on the xz plane. The z-axis will be perpendicular and coming out of this, right, like this. So we have placed the object in the right circular cone on the xz plane such that its axis coincides with the y-axis, so that the center of the base is coincident with the origin of the coordinate system. So if you look at it from the x-axis perspective, half of the cone is the positive direction, half is in the negative direction. Since it's a uniform cone, so the both sides will be equal, the masses of both sides will be equal, and so the center of mass will have to come to the origin. With respect to the z-axis also, since the base is standing on the z-axis also, it's symmetric about the z-axis, so the z coordinate will also be 0. So what we mean is that x cm equal to 0 equal to z cm. So what we need to find is y cm. What is the y coordinate? Okay. Now to do that, what we will do, like the previous cases, we will again consider a small elemental disk here. Okay. Sorry. Okay. And let's say this particular disk is at certain height. Let's say this height from origin is y, and its thickness is, let's say, dy. Okay. So if you consider with respect to x-axis, this disk that will be formed will have the, let's say, this is x, radius of x. Oh, this is not r, sorry, this is twice r. And this length, as we know, is r, and so is this length. So OD is r, Let's say call this point B and let's call this as the center of the disk we have drawn for our purpose. So what is the mass of this elementary disk of which is at a height of y from the y xz plane and has a thickness of dy? What will be its mass? dm will be mass of the disk, which will be pi x squared dy multiplied, this is the volume multiplied by the density of the material, if rho is the density of the material of the cone. Right. Now, since we have to integrate along the y-axis, we have to convert this x into y. Otherwise, it will be difficult for us to, or will not be possible for us to integrate this, right? So to do that, what we will do is that we will look at the geometry of it. Let us say delta ACB and delta AOD. These two are similar triangles. Why? Because this is the common angle, and this angle has to be right angles. Angle O and angle C. These two have to be right angles. So, if two angles of two triangles are same, then they have to be similar. If it is so, then what we must have the entire length, right? Say AO, that is H divided by AC, that will be, so if this is Y, this will be H minus Y, must be equal to this length, this is R, divided by this length, which is X. Right? Which will give us X equals to R into H minus Y divided by H. Therefore, dm will be, substitute the value of x from this equation, will be pi r square h minus y whole square by h dy, and then rho will be there. So if this is dm, then what will be ycm? It will be 1 by m integration y dm. Y is from 0 to the height h. Okay, so if you solve this, I am not going to solve this equation. You substitute the value here, do the calculation, open up the h minus y whole square formula. Whatever constants can be taken out, first take them out, then open up the whole square formula, then integrate it, substitute the value of h, and please remember what will be the mass m. Mass of the hemisphere, oh sorry, not hemisphere, mass of the cone will be simply volume of the cone, that is 1 by 3 pi r square into h, right? Since it's a right circular cone, so it is this multiplied by rho. Substitute this value of m here after you have integrated the whole term and simplified it, and you should get y cm should be equal to h by 4. Please solve this at home and let me know in comments whether you have been able to find this solution or not. Right circular cone, the coordinate of center of mass will be this h by 4, 0, where h is the height of the cone. Okay.